given all those problems. Let's see. Recording. Test. Alright, I hope it works. It seems to be working. Alright, so I want to work one of the test problems. Before I do that, today we're going to talk about AC behavior, the diff amps, how to calculate AC gain, common mode gain, all that stuff. Then Wednesday we'll do voltage references, basically band gaps. And then after that we'll move into chapter 24 and talk about op amps. And why is my computer doing that? I'm worried the video. Alright, I'm assuming it's okay. Talk about op amps and spend the rest of the semester talking about op amps, which is what you need to learn how to design to do the projects. Okay. The projects are right here if you didn't see them. Now, you're supposed to design the CMOS replacement for the LM386 audio amp. That doesn't mean you can go look at the schematic and say, oh, I'm going to do a transistor replacement. Yeah, I mean, it's bipolar technology. You need to design a CMOS op amp to replace it. And this circuit was probably designed in the 70s, my guess. And so technology has evolved and we know how to design better now than we did back then. So you should be able to do better than what's designed here, okay? Let me see, anything else? The course projects, or the lab projects, have also been posted. And again, I will be traveling the next 2 Fridays, so Yian will be supervising the labs, but everything's laid out here. Or you can see here's the project, which isn't due until May 8th, so it's due a month from this Friday. It's to design a band gap reference. So your course projects design an LM386 audio amplifier, and your lab projects to design a band gap and reference and test it out. Okay, so everything's laid out nice and organized. Of course, if you don't look at it, and what can I say? You know, when are you going to sign the projects? I don't know. When should I? Oh, wait, I already did. Okay, so I made an extra lab at the end because last time I taught this, the lab was offered on Monday. There were more holidays on Monday. So we have the extra lab here, lab 9. Okay, any questions before I work problem 4 from the test? Yes? You're creating a replacement for the audio amplifier. I don't know. The thing is, when I look and I grade your projects, I'm not going to be, oh, did they follow every single thing? Oh, they didn't put an enable or whatever's there, the extra feature. I don't care as much about that as that you've demonstrated you're not doing monkey see, monkey do, which is a big problem anymore, where students, oh, well, I'm going to copy that and then just modify it a teeny bit, and that's instead of original thought. I want to see that you understand what's going on. You can answer questions after you finish this class. So if you go for a job at Qualcomm or wherever, and they put you in the room and they say, tell me about some project you worked on. Oh, I designed an audio amp. And then they start asking you questions, and then your response are, I don't know, I just copied that from the book. That's what I don't want. And that's what happens a lot. I don't know, I didn't really think about that. I just copied what somebody told me. Well, you just wasted your time, right? So I don't want to tell you, oh, do this or do that. What I want you to do is demonstrate critical thinking and independent thought. Does that make sense? No, I just want to do monkey see, monkey do. You know, it's like some of the professors, they'll do this. Nobody in this department, obviously, but they'll say, okay, if x plus y equals z, x is 10 and y is 11, z equals what? 21. And then they'll say, okay, well, now you do it with x equal to 9 and y equal to 12, and what do you get? Well, there's no critical thought there, right? It's just you plugging in the numbers and, oh, well, okay, this is ridiculous. This isn't engineering. Okay, I don't want to do this. I want you to be able to think about what is, even if your project doesn't work and you've tried some path and you've experimented and you've tried to do something and you can articulate what you've done and why you went down that path, you'll get a good grade. Okay. Now, if it doesn't work and it's because you don't have any clue and you didn't put any effort into it, I've been doing this a long time and I can really spot that quickly, all right? My fluff meter goes crazy, okay? And I have a good fluff meter. All right, any other questions before I work the problem? How was the test? Well, I've got the whole test here. If there are any other questions, we can work it. But, I mean, this one, I think, this problem's really easy. And then after I graded it, I'm like, what the hell? I guess I didn't do a good job explaining concepts. I mean, this problem's super, super easy. Okay, so I'm going to go through it right now, and we're going to go and describe how to solve it. So it says estimate the gains, blah, 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 using R out cascode, R out P. And then I said you could also use R out cascode besides NP. I told you that before the test. You can assume the small signal resistance looking into the drain is R out P. The source of M2 looking down is R out P over 2. Okay, so does everybody see when I look into the source of M2 and I say the output, the resistance looking into the source, ROP over 2, is ROP over 2, that means there's a resistor of ROP over 2 to ground right there? No, you don't know that. At least 99% of you. Okay? Because you made some crazy stuff and I was reading the test and I'm like, what the hell is all this math calculations? This is ridiculous. So then I go, this is GM VN, and this voltage here is VD2T. So then I write VD2T equals minus GM VN times R out P in parallel with R out P over 2, or VD2T over Vn equals minus GM R out P in parallel with R out P over 2. First one done. That test was long. Yeah, it was long because you didn't know what you're doing. Okay, any questions on this? So let me see. That takes care of this one. Now let's change colors. I want to calculate the current that flows down there. Let's call it IX. And I'm going to write the current that flows down there, IX, is V out equals, so it's flowing down and it flows into that resistance. That's what's flowing through this device. So that's equal to IX times R out cascode N. Tell me how to calculate RIX. Let's go ahead and sketch it. That's the current through there. So we get a current that flows through here and a current that flows through there. Of course, it's going to be negative if I put these currents going out because all three are going out. How do I calculate the current that flows in that resistor in two parallel resistors? From circuits 1, like the third week. What is this circuit called? Current divider. So let me see, the input current is okay, so minus GMVN, this is scaring me, so I'm going to derive this, times what for the current division? ROP plus, ROP over 2. So let me pause and go back here. Call this IX. Let's call it I. Let's call IN. And I want you to show me how to calculate the current that flows through there, IX. Okay, so what's the answer? IN times the current through here is R1 divided by R1 plus R2. Okay, that's one of these equations just like this one, V. What is this circuit called? Voltage divider and attenuator. Drops an input voltage down. So it's Vx is R2 divided by R1 plus R2. Ix is IN times R1 divided by R1 plus R2. Has anybody not seen that before? So let's derive it. Tell me how to derive it. Oh, so you got a degree in electrical engineering. Let's start with some circuits 1 stuff. Here's a current divider. Show me how to find out the current through Ix through R2. What is it? So label this node, say Vx. Then you say IN equals Vx over R1 plus Vx over R2. Vx equals IN times R1 in parallel with R2. Or would everybody be okay if I wrote that as, what is R1 in parallel with R2 equal to? Tell me what to do now. Here, I'll help you out. And let's just write it as 1 over R1 plus 1 over R2. Tell me what to do. Of course, it is long if you have, the test is long if you have to go derive a voltage divider or a current divider from scratch. So would everybody be okay if we took this value of Vx and we plugged it in here? So we could write oops, no, I don't want to do that. Ix, oh no, I want to solve for Vx, so I want to take this value of IN and plug it in there, and I get Vx equals, oh no, I don't want to do that either. Maybe I can't derive the voltage divider because it divides out. Let me think here. Vx, IN, R1 parallel. What's that? Yeah. So Ix equals Vx over R2. Oh, we're done then. All right, that was easy. All right, so then we plug Vx in here, which is Vx equals R2Ix. Plug that in here, and we get IN is equal to R2Ix times 1 over R1, 1 over R1 plus 1 over R2. Yay? I did that right. IN equals Vx times 1 over R1 plus 1 over R2. Yep, that's right. This is Ix. And last but not least, Ix equals IN times, we can multiply through that, R2 would be 1 plus R1 over R2, but then we move it on this side and flip it, and that gives us R1 over R1 plus R2. It's been a long time since I derived that equation. Since last summer, I think. Any questions? So does everybody understand this? So then we go up and we say V out over V in equals minus GM. And then what could I... we'll do it in 2 steps. Equals what? Oops. Well, what happens to the R out P's? Right, they cancel. And that becomes 1 over 1 plus 1/2, or 1 over 2 over 2 plus 1/2, or what? Yeah, 2/3. Then I put my box around here. Any questions? What was the last one? V out over VD2, V out, oh, well, you can get those by multiplying these two together. Flip this over, so you get VD2 over V out. So then this would be V out over V in divided by V in over VD2. Now R out P's cancel once again, so you could probably simplify that even more, but let's see, the V ins cancel, and that gives me, if I did that algebra real quick in my brain, that would be GM squared. R out P in parallel with R out, I think it's the same thing, so I think it's 2/3 squared. I'm willing to take a chance. I'm sure the grader would be so happy to see a solution like this. Yes? Yep. Yes, I did. Thank you. But I'm so happy to see something like this, the joy. Oh, well, they know the resistance looking into something is a resistor to ground. So this one I thought was a gimme. And then I realized I failed you. All right, any questions on this? Any other questions from the test? If you think I graded you wrong, please write it down, turn the test back in, and I'll make sure I grade problem 5 really well too. Chances are you won't be happy when you get your test back. And you'll be, nah, that's too nice. You'll be very unhappy, in fact. All right, problem number 1. Come on. Come on. This is ridiculous. And what it's going to be on the final? Can I do the same one? I seriously don't know how, what I could do. Let's see. Let's look at this. Let's see. There's that problem. 200 megahertz, 1K, 1 pico. That's a 1 nanosecond time constant. The test was open book from chapter 1. .200 hertz, 1K, and 1 microfarad. Come on, man. It's ridiculous. Well, I agree, you don't. All right. Okay, so let's talk about diff amps. All right, I'm not going to go over the DC part again. I don't know what to say. Does that problem seem more reasonable now that I did it? Does it seem like when I do stuff it's easy? You know why? Crap doesn't clutter my brain. Everybody's like, what's that? You like PowerPoints? All right, I'm going to do this several times, okay? Now, you've already seen this basically from example 9.5, so this should be somewhat of a review, but I'm going to go through this several different ways for the rest of the lecture today, and then I'm going to do inputs on each side, and I'll do a PMOS flavor, so I'm going to do this over and over again. So I want you to follow what's happening. So what's the AC voltage here? 0. What's the AC voltage there? Yep, everybody agrees. How much AC current flows through there? Anybody not follow that? I'm going to label this current ID1, this current ID2, and then I'm going to write plus minus VGS1 plus minus VGS2. Then I'm going to write a KVL. So I get a power up, V in, power down, minus VGS1, power up, plus VGS2 equals 0. You see how easy it was for me to write that? You will think that's easy. When you leave today, go do it yourself and put it on this side, and make sure you can do it on both sides, okay? Any questions on that? All right, so I could write V in equals VGS1 minus VGS2. Now, no current flows through here. So what this means is if I have 20 microamps, I'm repeating myself because you've already gone through this. If I have 20 microamps flowing in here, and there's 1 microamp of AC current, it means the current goes from 20 up to 21. The AC ID1 is 1 micro. This current goes from 20 to 19. So we have 21 and 19 flowing in each transistor. So I say ID2 is minus 1 microamp. And you say, hey, that means the current's actually flowing backwards. It can't flow backwards through the MOSFET. Well, it's not. The AC current flows backwards, but the overall current is still flowing down. It's just a decrease in the DC. We all remember that from example 9.5? Okay? So, what can I say about the AC current here and the AC current here? Equal and opposite because there's no extra current. So I can write ID1 equals minus ID2, or ID1 minus ID1 equals ID2. And you think I'm joking on that problem 4 when I said I failed you, but it was clear that I didn't teach that concept well, because you should have all slam dunked that one because that's an easy problem. So in the future, I made a mental note. Every time I talk about resistance looking in, I'm going to pause and I will ask, if I say the resistance looking into the source of M2 is ROP over 2, what do I replace all this circuitry with? ROP over 2 to ground. Boom, you're done. No deep thought. That's what that's why we talk about it all the time. The resistance looking into this node is this. You replace that node and all the circuitry that follows with a resistor to ground. Okay? Just like that regulated drain cascode. You got an op amp and you got a cascode structure and all that. That's why we talk about this, because it simplifies life. Okay, what equation pops into your head when I look at these? Yeah, GM-VGS equals ID. So I can write VGS equals ID over GM. Or I can go back here and write Vn equals ID 1 over GM1 minus ID2 over GM2. Does everybody agree with that? VGS1, VGS2. Okay? So now, I know ID1 and ID2 are equal and opposite. I can rewrite this as VN equals ID times 1 over GM1 plus 1 over ID1 GM2. Does everybody agree with that? So does everybody now notice, because ID1 is minus ID2, I pulled ID1 out, that these are both positive, but what can I say about GM1 and GM2? They're equal, right? Because I'm biased each one of these at some point, and then I'm wiggling back and forth. When this one's increasing, this one's decreasing, but I'm assuming small signals, and so that the GMs of the two devices are equal. So I can rewrite this as Vn equals ID1 times 2 over GM1. Or ID1 equals GM over 2 times Vn. Or ID1 equals GM times Vn over 2. How is this relation, and we could put 1 here if you wanted, how is this relation related to the transistor's VGS? Vn over 2 is equal to VGS. Does everybody agree with that? So if I ask, what's this voltage here? We just showed it's Vn over 2. Similarly, what is this voltage? Keeping in mind plus minus, and then also keeping in mind when this node goes up, what happens to the current in this stage? If I drive the gate up, what happens to the current? It goes up, turning the device on. If I drive this up, what happens to this node? It goes up, pulling everything up. If I drive this up, this goes up. What happens to this node when I drive this one up, and why? Keep in mind there's a voltage source connected to it. Nothing. It's held at VCM. Does everybody see that? So wait, if this node goes up, what happens to the VGS2? It goes down because the gate's staying fixed and the source is going up. So VGS2 is equal to minus Vn over 2. So then if I write here, VGS1 is Vn over 2, VGS2 is minus Vn over 2, what is that sum to? Vn. So I went through a bunch of wah, 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 wah. Key point, if I apply Vn on one side, VGS over 2 minus VGS over 2. Or I could write it like this, just to be different. Plus minus VGS over 2 plus minus, like this, VGS over 2. But notice plus minus is opposite of plus minus this way, so it's minus VGS over 2, Vn over 2 this way. Whoops, sorry. This should be n, Vn over 2. Does everybody follow that? Okay, so clear your brains for a sec. If everything's in saturation and I apply Vn here, half of it drops across like that, the other half drops across like that. But because of the way that we define VGS here, because it's going plus, minus, that's a minus Vn over 2. Any questions? Let's do another one. Let's continue before we finish this because we're almost done. This is the hard part. This part's easy. So what is this current flowing here in terms of Vn? Gm Vn over 2, because that's the current flowing through there. Any questions? So what is the VGS of this device? VN over 2. So that flows through here, but this is a current mirror. So what's the AC current flowing there? It's a current mirror, it mirrors it. GM/VN over 2. What's the current flowing down there? It's got to be equal and opposite to this because there's no current flowing here. So this one is minus GM/VN over 2 because this VGS is minus VN over 2. But I could think of it, instead of flowing down, as positive GM/VN over 2 going up. And yes. So let me continue and make a nice clean schematic on the next page because that one's really nasty. Here, what you can do, you can take this and print it out, and then you can put it on your fridge and you can say, this is what I learned in school today. Then people in your family will feel sorry for you and make you a nice dinner. All right. So let me draw. I'm going to not do anything different here. So I'm going to draw the same. Or you could be like my wife will say, it's your choice. She has a good sense of humor. VN over 2. VN over 2. Does this look right? So what's the current flowing there? GM/VN over 2. What's the current? I'm going to draw it going up like this. GM/VN over 2 because it's ID2 is minus that. Or the current flows down. It's mirrored across. What's the current flowing here? GM/VN over 2. Does everybody agree? Anybody not follow this? Because this is we'll use for the rest of the semester in op amps. GM over 2, we can go ahead and write it here. GM/VN over 2. Mirrored across. It's going in. This node goes up. The current in here goes up. Current here shuts off. So I get 21 flowing through here. 21 flowing through here. 19 flowing through here. Net current into the node, 2 microamps. Because I got 21 coming in, 19 going out. Am I going too slow? So, what's the resistance I see looking up in there? ROP, right? That means this device I can replace with a resistor to ground of ROP. And forget about all the other circuitry over here. See how I evolve when I learn to teach? If I ask what's a good estimate for the resistance looking down there, well, this is actually a pretty low impedance node, so I'm going to approximate the resistance looking down as RON. So ROP, RON, so the total current that flows here is what? Anybody not follow that? And so this will be V out is equal to GM VN RON in parallel with ROP. Or V out over VN equals GM RON in parallel with ROP. We've just done AC. Why is it what? The resistance looking down in here. If this was ground, right, then that would be precisely RON, right? But it's not ground, it's a low impedance, so I'm approximating the resistance looking down is RON. Remember, I don't want to be too academic because my RON does this. So I say, oh, it's this value, but then I have actually a larger VDS, it moves up here. Any questions? So in your op-amp designs for your projects, your first stage is going to be a diff amp, just like in the bipolar version of the LM386. This is how you calculate the gain. Any questions? Okay, I got a question. Qualitatively, explain to me why the gain is positive. So if this node goes up, what happens to the current in this stage? Goes up. What happens to the current here? Goes down. That's mirrored over here, so I get more current flowing in, pulling. Remember I had 21 and 19? That pulls this node up till the two currents are equal again. Or if it's an op-amp, till the inputs go back to the same voltage. So if this current goes up, it's coming over here, this goes up, and so this is the positive input. This is the minus input of the diff amp. Because if I yank this node up, what happens to the current here? It goes up and it pulls the current this way. Okay, so I'm going to do this problem again. Any questions? Except I'm going to modify it a little bit so it's not so boring. So let's draw it again. And I'm not going to put the DC biasing in the current source and all that. So it's the same circuit, except I'm going to connect it a little bit different and get a more generic gain. I'm going to call this, how about VP? Again, I'm not showing the DC biasing. VM and V out, and I want you to calculate V out over VP minus VM. This could be the positive input or non-inverting input of the op-amp. This could be the inverting or minus input of the op-amp. Note, when we put another stage on the output of the diff amp that's inverting, what happens to these two terminals going to the output of the op-amp? If we put a negative gain stage connected to the output here to boost the gain, then they flip. Okay, because although under any circumstances, if this one goes up, this output goes up. If that's going to an inverting stage, that'll cause the output of the op-amp to go down. Does everybody follow that? So if I represent this diff amp like this, plus, minus, here's the diff amp, and then I put a negative gain stage there, and I call this whole thing the op amp, what happens here? Yeah, this becomes the this becomes the negative, and this becomes the positive. Any questions? So you don't ruin your lives in hours because you forget to flip the plus and minus and your op amp won't bias up right. None of you will do that, right? All right, good. Okay, so tell me how to find the gain. Let's start out by, this is exactly the same way I did before. Let's label the VGS's. Plus, minus, plus, minus. So I'm going to write this. I want you to do it with me. We'll start going this way. I'll start you out. VP minus VGS1 or VP minus VM equals VGS1 minus VGS2. And you know what? Shh! Guess what? These two voltages are going to divide equally across here. They have to, because the currents are going to be equal and opposite in each side. Yeah. All right. So, would it be okay with everybody if I went VP minus VM equals ID1 times let me think. Let's see if I did that right. The IDs, whoops, I got this is not this is GM. I got the ID is equal to GM VGS. So if I substitute the VGS's in here, I get ID over VGS. I'm sorry, I get ID1 over GM1 and ID2 over GM2. Does everybody agree with that? Okay, so let me go through here and do it step by step. VP minus VM is equal to ID1 over GM1 minus ID2 over GM2. That's equal to, oops, I got them, this thing should be flipped. That's equal to ID1 times, does everybody agree with that? Wait, how do I know that? GM1 equals to GM2. ID1 is equal and opposite to ID2. Does everybody agree with that? So then I can go over here and I can go, okay, well that says this current is VP minus VM is equal to, or this current is times GM1 over 2. Or if I call this Vin, it's Vin times GM over 2. Oh, wait a sec. That's exactly the same thing we had before when we just had Vin over here. All I've done is I've replaced Vin with VP minus VM. So what's the current here? GM over 2 times VP minus VM. What's the current flowing up there? Flowing up. Same thing. What is it flowing down? Yep. And then what is V out? So what is V out over V in? It's V out over VP minus VM, which is GM times R out N in parallel with R out P. Same exact thing. No, because this current is GM over 2 times Vn. This current's GM over 2 times Vn. So this current plus this current's GM times Vp minus Vm, or GM times Vn. And then that... oh, here. All right, thank you. I was just checking to see if you were paying attention, or everybody's like, damn, I wish it was still spring break. Why does he make the first lecture back from spring break so much writing? All right, any questions there? Okay, I got a question. What if VP and VM are equal? They both go up together and down together. What is the output? It stays the same ideally, right? If both go up by 10 millivolts, that means this node goes up by 10 millivolts, so the current in each side doesn't change. But I want to explore that in more detail. Does everybody follow? If VP and VM are equal, then the gain ideally goes to 0, because the current goes to 0. Any questions? Well, wait, I'm dividing by 0. Pause. VP equal VM. This is 0, so V out equals 0. Remember the old math trick you might have learned in like 8th grade, where you do those things and you say like 1 equals 5 or something, and it's because at one point you divided by 0. We don't want to do that here. We're going to go back one step where VP is equal to VM, and then that gives V out equals 0. Yay? Alright, so we ready to explain that? And this is called the common mode rejection ratio. It's a very important parameter for op-amp design and high-speed signaling. Like, does anybody know what LVDS is? And like your cell phones, the communication between like the CMOS imager and the image processor, or the DRAM and the processor. It's low voltage swing, differential swing, where one of them's going up and the other's going down. So if there's any noise on the two lines, it gets rejected by the common mode rejection of the op amp or the input. So that's what I'm about to talk about. So it's not academic crap. This is useful. The noise cancellation is a little bit different. The noise cancellation, what it does is it measures the ambient noise that's repeating and then feeds back a signal that's equal and opposite out of phase. So it's a simple, not simple, they have really complicated things now, but it's a digital filter. So this is just rejecting a common signal. And I'm going to go over it qualitatively first just to make sure you know. I'm going to repeat what I just said. So here's my diff amp. So this is qualitative, and then we'll do the equations. You guys sure you don't want PowerPoint? PowerPoint's nice. PowerPoint tests, yes. How about I draw it a little bit different? Okay, so noise. So when they design, like in your board, your motherboard, your computer or your cell phone, whatever, and they transmit the signals and they transmit them some distance. There's generally about, I used to know this better, but like 100 picosecond propagation delay per centimeter on the printed circuit board. When you transmit the signals, it can pick up interference. Okay, so if these two nodes, because of there's lots going on, so there could be something coupling into the two lines, the two wires here. So the common mode, okay, so we're going to use this a lot, and it's used in industry a lot, is nothing more than the signal that's common to both wires. Okay, so a common problem that you might have already encountered in audio or in your labs or whatever is like a 60 Hertz hum. So you have like the wall socket here and you have wires that are going around. They can radiate noise into your speaker and you can hear that hum noise. You know, that noise, that's picking up. So if you go into your diff amp and that's moving back and forth, this will ideally reject it. So here, let's go through and explain that. Okay, so let's say this is 40 microamps DC. This is 20. And this is 20, obviously. And then how much flows down through each of these? Okay, these are questions I'm feeding you. They should be, boom, there it is, and you have an answer, all right? It should be, let me think about that. What's the current flowing down through here and here? 20, okay? It's following, there's no other place for these currents to flow. It's got to be 20, right? So they're flowing down through there. Let's say that these two voltages are 2 volts. That's the common mode voltage, and so let's just assume this is 1 volt. Say I got a huge 60 Hertz hum. So this common mode voltage goes up to 3 volts. What's the current flowing through each side here? Still 20. What's this voltage become here? 2. Well, if I have the same current flowing through each side, I got to have the same VGS. If the VGS is the same, this just goes up with the input common mode voltage. If that's the case, and I got the same current flowing through both sides, how does V out change? It doesn't. It stays constant. So even though I got that noise bouncing back under that common mode signal that I don't want, it's not appearing in the output of my diff amp. So I'm not going to amplify that, and I'm not going to hear it. And this is why they use fully differential signals. Also, they can reduce the signal level because they don't have to worry about noise, so your signal-to-noise ratio stays high. Very, very, very common circuit. You probably have thousands in your phone right now. Any questions? Now, in reality, this assumes the current source is perfect. And we know the current source is not perfect. We know there may be some parasitic capacitance, or if we used a simple transistor, we would just have R out, or R out cascode, whatever it is, right? So if I were to, in a real current, in a real circuit, if I were to increase this from 1 to 2 volts, what would happen to the current in here? It would go up, because I'm increasing the voltage across that current sink. If it goes up, then the current on each side here goes up a little bit, and my output will change a little bit. And that output over this common mode signal is called the common mode gain. And what do we want the common mode gain to be? 0. The common mode rejection ratio, which is in dB, is the ratio of the common mode gain to the difference mode gain. For a diff amp, what's the difference mode gain? Please say this because I just derived it for you 2 times at least. Yeah, GM times R out N in parallel with R out P. Any questions? So let's calculate AC. But before I do, does everybody qualitatively understand what why diff amps are used and why they want to have common mode rejection? Yay? Okay. So what I'm going to do is I'm going to apply a common mode signal to both gates. It's the same signal, and I'm going to call it to VC. And then I'm going to replace the current sink with a resistance which models the output resistance of the current source. So I have the following. I'm not showing the DC bias, but if you want, we could draw that on here. We'll just call this VC. And let's just call this R out. And here's V out. So this is for calculating common mode gain AC. Okay, so before we go too far, what can I say about VGS1 and VGS2? They're equal. They're no longer equal and opposite because I've got the gate potential the same and the source potential the same. If I call this current ID, what's the current in here? ID. What's the current in here? ID. Wait, but now this circuit and this circuit are mirrored. They're exactly the same. What's the current in there? ID. Okay, we'll come back to this in a minute, but now I no longer have 2 ID going into the node. I have ID going in and ID going out. So now I want to calculate ID. Any questions before I do? Does anybody think I can? Or are you thinking, no, he's not going to be able to do it? Can't do it. The stress. Okay, so I'm going to write a loop here. VC. How about if I just write instead of VC minus VGS1 minus 2IDR out, I write VC equals VGS1 or 2, because they're the same. Boom, boom, or boom, boom. Plus, and what's the current flowing in R out? Think, what is it? 2ID. So what do I write here for the last term? Yep, R out times 2ID. Would everybody be okay if I wrote this as ID times 1 over GM plus 2R out, or VC is approximately ID times 2R out? Would that seem reasonable, that if R out's much, much larger than 1 over GM? Yeah. Everybody agree with that? Any questions how I wrote that? Okay, so but what is V out? I no longer can say, oh, the resistance here is R out, the resistance here is R out N, because now I don't have any net current going into whatever the resistance is there. The net current into the node's 0. So what goes in comes out. Okay, so here's the trick. I have the same ID flowing in each transistor. I have the same VSG in each transistor. Why? Physically tied together. But wait, this is a gate-drain connected transistor. So what do I know about the source-to-drain voltage of this transistor relative to the source-to-drain voltage of this transistor? What do I know about the voltage wiggle here if their VSG and ID are the same relative to here? It's got to be the same. The IDs are the same, the VSGs are the same, then the VSDs have to be the same. But hey, this is just a resistance of 1 over GMP. The current that's flowing through there is ID. So because of the symmetry, does everybody follow that? You can prove it in SPICE. This V out has to be minus ID times 1 over GMP. Does everybody follow that? No? Let's forget about this part for a second. Does everybody recall, because I went over it numerous times, that a gate-drain connected transistor small signal impedance is 1 over GM. Or if you want to be precise, 1 over GM in parallel with R out, but that's approximately 1 over GM. Right? Everybody agree this VSG and this VSG are the same. This ID and this ID are the same. So if you have the VSG and the IDs are the same, the drain to source voltage. That was the #1 rule when we talked about matching. So then V out has to be the same voltage as this one, which has to be minus ID times 1 over GMP. So my common mode gain, any questions? Am I writing too much on the pieces of paper and it's getting too cluttered? I need to use like one of the markers from the board with a thicker tip. Limit the size. Okay. AC is V out over VC, and that's equal to minus 1 over 2 R out GMP. Any questions on how I derived that? Dwayne. Nope. When we're doing this, or when you're designing op amps, you assume that everything's operating in saturation. If it's not, then all these calculations in the small signal approximation don't work. So remember when I started drawing this, I said I'm not going to draw the DC bias. I'm going to assume this it's replaced with its small signal, so I'm only going to talk about AC gains. Does that make sense? So I assumed that I've got a DC common mode. If you want, we could go here. We have to have some common mode voltage that biases everything on. Because if you don't, this is one of the things for me that was a big struggle when I was learning, because I was like, well, how does that work? If this is at ground, isn't that device off? And then I finally realized, don't fight it. You have to move everything so that it's biased on. Once you move everything you bias on and you don't try to fight that, then life is good because things aren't shutting off and things work. All right, so I've got some questions. What, again, remind me, was the ideal common mode gain? 0. Okay. How would I, looking at this equation, what's the fundamental way that you increase the common mode rejection ratio? You increase the impedance of the current source here. So if you increase that, what ends up happening is that your common mode gain goes to 0. So let's say I used a regulated drain. So what does regulated drain mean again? Remember, it's one of those sources that does this, where you have that extra bias and then it acts to hold this node, so then the output resistance becomes GMR out squared times the gain of the amplifier, so it shoots up to a super high value. Let's say I make A huge, 10,000. So I've got a huge output impedance, and you say, wow, I've got really good common mode rejection. I'm not going to have to worry about any coupled noise unless it's so large that it shuts your devices off because they're moving into triode. Well, okay, so here's the problem. If you do that at a certain frequency, the parasitic capacitance here starts to become an issue. So it starts to become an issue, and then instead of this dominating the impedance at the node, you start getting a displacement current through that capacitance. So the common mode rejection ratio starts to die or fall off. Not at Okay, so what that means is I would like my common mode rejection ratio at a gigahertz to be high, because if I have any coupled noise from a microwave or whatever, it doesn't couple into my circuit and mess my circuits up and I start making bit errors or mistakes, okay? In reality, this capacitance will drastically lower the common mode rejection. So let's just pause for a moment and go look at the, where is the projects? Let's look at this, and let's look at common mode rejection. So this is a PNP input pair. Let's see. Talks about input biasing. Common mode rejection. Where's common mode? Let's just do a control F. CMRR. What? Common. What kind of crappy? Whoops. Maybe I didn't give a good data sheet. Let's go look. See how many pages it is after the... Alright, voltage gain, distortion. Yeah, this is an old amplifier. It may not even have common mode rejection on it. Well, did we use a different one in lab? What's that? What? Op amps. Alright, let's look at the lem324. How could you? Oh, we used the lm386, but it was a different data sheet. Okay. Alright, let's go look at this one. Common mode range. What is that? No, they didn't use common mode CMRR. That's a typo. But here you see, okay, there's it goes up to 80 dB. Let me see if they have a plot. Common mode rejection, and they're only going out to a megahertz. If they went out further, you would see the common mode rejection ratio falls off. And so at high frequencies, you don't get good common mode rejection because you get the current through the current source. Let's see. I almost had you do this equivalent, but then I thought, yeah, it's too easy. They need something that's tougher. Alright. I don't see a better specification than CMRR. Their plot only goes out to a megahertz here. Alright, so any questions on this before I do some examples? No? So, in the homework problems that are due on Wednesday, you should be able to calculate the AC gain of the, I was going to do PMOS, but we're running out of time. The AC gain of the diff amps, you should be able to calculate common mode rejection if that's asked as well. And then you should know how the slew rate and the common mode range and all that from already our discussion. So let's look at a few sims and then we'll call it a day. So let's look at common mode rejection. CMRR. Let's look at 2216. And here's more of a discussion on common mode rejection. Very important issue. Okay, so here I want to make sure everybody follows what's happening. I've got the 700 millivolts is the common mode voltage. Here I have an AC input of 1 volt, so I'm connecting a common mode voltage of 1 volt to one input here with an AC signal of 1. Over here I'm tying the two inputs together, so here I'm going to calculate the common mode gain. Here I'm going to calculate the difference mode gain because this other input has 0 AC on it. So this will give me V out D over V in. This will give me V out C over V in. And then to get the difference mode or the common mode gain, it's V out C over V in divided by V out D over V in, or just V out C divided by V in. So we can hit run. And there we see starts rolling off. Nice little common mode gain. I want to do a simple example, or before I even do that, let's show you the, did I write it backwards? Is it V out D over, yeah, it's V out D. Did I write that backwards? Yeah, I wrote this backwards. Or upside down. It should be, oh no I didn't. It's V out over VC. Where did I write the common mode gain? This one's backwards. So that should be ID. I knew I wrote it backwards somewhere. That one. Should be the difference mode gain over the common mode. You want high common mode rejection ratio. Okay. So just to show you, there's the gain by itself. It's not that high. Why? Why is the gain only 25 point whatever dB? It's a simple single stage diff amp. That's why we need to have two stages to have an op amp, because remember, an ideal op amp has infinite open loop gain, so we get the higher gain by cascading. So just as a sanity check, if this gain is 30 and the next stage gain is 30, what's the overall op amp gain? 900. 30 times 30. That's why we cascade the stages, right? Okay, so I want to just real quick tell you, if I go back now and I get rid of this current source here, or actually, yeah, we'll just do it this way. And I do this, everything will still buy, oops, edit, undo. Everything will still bias up effectively the same, right? Because now I've still got the same current, still set by 20 microamps or 10 microamps, this is the short channel, through the current through these two transistors, right? What do you think is going to happen to the common mode rejection ratio? Well, according to the equation I derived, it's going to drop because now my current here, my output resistance is R out instead of R out cascode. So I go look and I say, ooh, now it's only 56 dB instead of 80 whatever it was. Okay, so let's do one more. I know everybody's like, I want to go. All right, so I run it again. There's the 80 dB roughly. If I put a capacitor on each one of these, and let's just say it's, we'll put 1 pico. And then I put one here just to make sure it's the same. And I ask, what's going to happen to the plot? Yeah, it's going to start rolling off sooner, right? Okay, Again, diff amps, they're used on the beginning of the input of the op amp. They're used everywhere, but they're used a lot in high-speed digital communications or anything where you have to reject a common mode coupled signal. Have a good day. We'll see you on Wednesday.